Hello. Can everyone hear me? Just type in the Discord if you can't, and I'll try to fix it. Should be better though than last time. Last time it was chopping up quite a lot. Should be better now. This is test stream. I'm gonna turn the stream off in a second and then restart it. This is just testing to make sure you guys can hear me. If you can, maybe like in the general chat or in the linear algebra. Okay, perfect. You can. And nothing's chopping up. Everything's good. Ivan, is it like cutting or can you hear me clearly? All right, good. Okay, so I'm gonna stop this stream, and I'll post the link in a second. I'm gonna stop this um and restart, or should we just continue? I guess. All right, good. Yeah. Let's continue. Let's not stop anything. Let's just start. Okay. So you guys should be seeing my screen now. Um, this is the online app that I use as a whiteboard. So let's start with um let's start. So I'm going to be using two books. The first one is this, which you should be seeing now on the screen. It's the Finite Dimensional Vector Spaces by Paul Helmos. I love this book, and the thing about it is that it treats linear algebra from, I guess, more of a mathematician's perspective rather than an engineer's, and that it covers the subject in terms of abstract vector spaces. Because linear algebra is, to me at least, the study of vector spaces and linear maps between them, as opposed to just treating vectors in R3 or some Euclidean space. So we'll cover some material from here, but I also want to make sure that we can compute. We can do computations with whatever we learn. So we'll do some examples of computing matrices, etc., for the people who are just getting into the subject. So let me start there. Let me start with what linear algebra is really about from the computational perspective, and then we'll abstract it away. So what it comes down to is we're trying to solve simultaneous equations. So here are two equations, very simple, right? I can have 2x1 plus 3x2 equals 5, for example, and I can have x1 minus x2 equals 0. So I have a system of that. We call this a system of two equations. Um, here's my equation 1. Here's my equation 2, and I want to find x1 and x2 that satisfy these two equations at the same time. And this is a fairly simple system. We can guess what the solution is, right? If x1 and x2 are 1, then we get 2 times 1 plus 3 times 1 equals 5, and we get 1 minus 1 equals 0. So everything's satisfied, everything's good. We found a solution to the system. Now, the systems don't have to be this simple, of course. We can have systems with many variables, not just two, and we can have many equations, not just two. So in general, what we can write is this. We can say we have some constant. I'm going to call this a subscript 1 comma 1, my first variable. So plus, let's say, a subscript 1 comma 2, the second variable, plus, and so forth. And then let's say a last one, n x1 comma n equals something. So let's call this b1. Okay, so that's my first row. That's analogous to this equation 1, but now I actually have, you see, I have 1, 2, I have n variables in this first row. And then I go to the second row. So a2 comma 1, x2 comma 1, plus a2 comma 2, x2 comma 2, plus dot dot dot, plus a2 comma n x2 comma n equals b2. That's my second equation. And then I can have as many as I want. Let's have m of them. So my last row will be a m comma 1, xm comma 1, plus am comma 2 xm comma 2 plus dot 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 plus am comma n xm comma n equals bm. Okay, so now we have a system, and in the system I have m rows, right? So that's m equations, and each equation has n unknowns. You see x1, x2, x3 per row. So we have an m by n system. And the goal of this system is to find these x's, okay? These x's that satisfy all of these rows, all of these equations. Okay, so how do we approach this task? Before we actually learn how to solve them, we're going to be using a very specific method called, well, we're going to start with this. We're going to start with this method called Gaussian elimination, and this is the procedure that which we'll use to find what those x's should be. But before we actually start computing, let me try to draw out something. This will be very helpful. Let's go back to our 2 by 2 simple case. So let's say I have an equation y equals, let's say x plus 3. Or let me erase this. Let's do something else. Okay, let's go to 2x1 plus 3x2 equals 5, and x1 minus x2 equals 0. Okay. So this was my original system. And what this system is a system of 2 equations, and we know how to graph these equations. Each one of these equations is a line. We can graph these lines. For example, the second equation we can rewrite as x1 equals x2, right? So you can think of x1, you can rename it if you want. You can think of it as y equals x. It's the same thing, except instead of y, I have something called x1, and instead of x, I have something called x2. And this is a line. We know what this line looks like. We'll try to draw this. There it is. It's this line with slope 1. Similarly, we can graph this line. This is also a line, right? We know that we can see that 1, 1 is a point on this line, because if I plug in 1 here, I plug in 1 here, 2 plus 3 does equal 5. So 1, 1 is a point on this line. There it is. And if you want, you can move things aside. You could move the 3x2 to the right side, and you'd get 2x1 equals 5 minus 3x2. So there's your slope right there, negative 3. Actually, if you divide both sides by 2, what you'll get is, let's move this here, you will get x1 equals 5 over 2 minus 3 over 2x2. So you can see your negative slope right here, and there's your y-intercept. So it's also a line. There is my y-intercept somewhere here. And suppose there's my line with negative slope. So if you notice, the point 1, 1 satisfies the second equation, because 1 minus 1 is equal to 0. And 1, 1 also satisfies this equation, because if I plug in 1 here and 1 here, I get 2 plus 3, and that equals 5. So this point 1, 1 is where these two lines intersect. It's the intersection of these two lines. So geometrically, solving a system of 2 equations like this comes down to finding the intersection of these two lines. And the reason this is important is because now you can say, okay, what are all the possible solutions? How many solutions to the system could I possibly have? In this case, I just told you one of them, 1, 1, but is it the only one? And is it always going to be only one solution, or is it possible for there to be many or no solution, etc.? And now that you know that solving a system of 2 equations comes down to finding the intersection point, the answer to that question comes down to asking yourselves whether we can draw 2 lines that don't intersect. And we know that we can. Here are 2 lines that don't intersect. If they don't intersect, if I were to write down the equations of these 2 lines, that system should not have a solution. I don't yet know how I solve this system, so I didn't tell you how I found the 1, 1, but whatever the method is, this system should not have a solution, the system describing these 2 lines here. And in a similar fashion, we can say, okay, is it possible for a system to have more than one solution? Well, again, we try to analyze this geometrically. We try to draw out such a case. So here are my axes. Here's a line. And now let's say, for example, suppose I want more than one solution. So I ask myself, can I draw another line that intersects this one at more than one point? And if you try to draw that, you'll quickly find that it's quite difficult to do. Any line that I draw will intersect at a single point, unless I draw the same line. If I draw the same line right over it, how many intersection points do I have? Infinitely many. So there are infinitely many solutions to the system that describes this case. What does a system like this look like? Well, we can write this. We can say x1 equals 3 plus x2. That's one line. And now I can just multiply both sides of this equation by a number. Let's say 2x1 equals 6 plus 2x2. I've multiplied both sides by 2. Now I have a system of two equations, but really they are the same equation. They represent the same lines. And so those two lines will have infinitely many intersection points, hence the system will have infinitely many solutions. And so intuitively, you can expect that when we learn to solve these systems, we will either have no solution because our quote unquote lines will not intersect, or we'll have one solution because, like in this case, they'll intersect at a single point, or they'll have infinitely many solutions because, like in this case, they'll intersect at infinitely many points. Okay. Now, so that's the computational part of this. Again, to recap, our goal is to solve systems that look like these, systems of many equations of many unknowns. And our goal is to find these x's that satisfy all of these equations. We have simple cases. Here are 2x2 simple cases. And the 2x2 is nice because we can graph them. They're lines. And as we saw in the example of these lines, we have three possibilities. Here is the possibility of no solution. This is the case when we have lines that are parallel. Here's single solution possibility. And here's the infinitely many solutions case. Now, to study linear algebra means to study this, to generalize this. Why do I want to generalize this? Because in this system of equations, I have familiar numbers. I have 2, 3, 5. I have 1, negative 1, 0. These are familiar numbers. It turns out that this doesn't have to be the case. Instead of having numbers like these, we can have whole functions, right? We can have polynomials, for example, or we can have other kinds of things. The only requirement that they need to satisfy is that they need to be what's called a field. So to understand linear algebra, we first need to talk about fields. What is a field? It's a mathematical object that satisfies certain properties. Now, the properties of a field are described in Helmholtz's book, so I'm just going to quickly go over them right here. So fields, that's exactly where we start, to start generalizing the subject. So for every pair, alpha and beta, of scalars, you can think of scalars as your numbers, 2, 3, 4, 5, etc. There corresponds a scalar alpha plus beta called the sum of alpha and beta. In other words, I can add two things such that, and here are three properties that need to be satisfied. Addition needs to be commutative. We know what that means. It needs to be associative. You can move the parentheses around. And there exists a unique scalar called a 0, such that if I add that 0 to any one of my numbers, my alphas, I get that alpha back. Okay, and also the fourth one is to every scalar alpha, there is a unique scalar negative alpha, such that they add up to my 0, to my identity. So if you look at these properties and they sound a bit abstract, let's try to relate this to the real number line. The real number line is a field. Let's write this out. Here's an example. Here's an example of a field. It's our real number line. So what was our first property? For every alpha and beta, the sum needs to also be in that set. Well, we know that if I take any real number and I add to it some other real number, we know that we get another real number. So this is what we call closure, right? You take two numbers, you do this operation on them, and you get another real number. So that's good. What we need to have is for that sum operation to satisfy these four properties, it needs to be commutative. Okay, so we know that if we take two real numbers and add them, we can add them in either order. I could do 3.1 plus 2. I still get 5.1. So we satisfy the commutative property. Addition is associative in real numbers. There does exist a zero, right? The real numbers do have this special numeral called zero, such that if I add anything to it, I get that thing back. Okay, so I don't change my result. That's 3 here. And 4 is for every scalar alpha, there corresponds a unique scalar negative alpha. We call this an additive inverse. And we know that for any real number, let's say 4, there exists an additive inverse such that they add to my identity, to my 0. For any real number you can think of, there exists its negative version. So this addition is satisfied. Everything that's listed, the properties 1 to 4, are satisfied for real numbers. What about B? So B talks about product. We need two operations. We need addition and we need product. So let's go over the product. So for any alpha and beta, we need to have a quote-unquote product, alpha, beta, such that it satisfies these four properties. It also needs to be commutative. It also needs to be associative. There exists a unique non-zero scalar 1 such that if I take any number and I multiply by that 1, I'm going to get that number back. Okay, so you might be saying to yourself, oh, I know obviously anything times 1 is that thing again, but realize when Helmholtz says 1, he doesn't actually mean the one that we know, not the number 1, but it's an idea. It's some object that when it multiplies anything else, that original number does not change. That original object does not change. And the real numbers do have this, right? The real numbers have a product on them. Think of any two real numbers, let's say 2 and 4. Here's our product that we know of. It is commutative. It is associative because I can move these parentheses. I could say 2 times 3 times 4. So commutative and associative properties are satisfied for any non-zero real number. Actually, we do have an identity, the 1, right? 2 times 1 is 2. 4 times 1 is 4. Any number times this identity 1 gives me that number back. And for any non-zero number, I have what's called a multiplicative inverse, such that when I multiply them, I get back to my identity. The 0 is the one that doesn't have it, because no matter what you multiply 0 by, you can never get 1. Your result will always be 0. So 0 doesn't have a multiplicative inverse, but any non-zero number does. And that's all we need, right? See, property 4 here says to every non-zero scalar alpha, there corresponds a unique scalar alpha to the power negative 1. This is notation for the multiplicative inverse, such that they multiply to your identity. Okay, so any mathematical set that satisfies these two things, is A and B here, is called a field. And the real number line is such a set, so we call it a field. So what do we need for a field? We need two operations. We need addition and we need multiplication. And those two operations need to satisfy these properties, 1 to 4, each one of them. Okay, so going back to our example here, when I wrote down this system here, my numbers that were familiar with the 2 and the 3, I'm getting them from the real number line, from this field. Realize, however, that they can be coming from different fields. For example, if you're familiar with complex numbers are also a field. Okay, and so these numbers could be complex numbers, or any other field that you can think of. These scalars, quote unquote, scalars, could be coming from that field. So in general, when talking about fields, we denote them with this F. saying that these can be any abstract entities from a field. Most times, however, we'll talk about fields. We'll pull these scalars from either the real number line or from the complex plane, just to keep things simple, so I can give you examples. Okay, let's go back to Helmholtz here. And another crucial part that I didn't mention actually is that for a field, multiplication and addition need to satisfy the distributive property that we've learned. So if you look at the example here, alpha times beta plus gamma, we can distribute the alpha in. And this is, we also know that in the real number system, the distributive property holds. Okay. All right. So let's do some of these exercises. Let's go over them so we see how this works. Understanding what a field is will be crucial to moving forward. So exercise 1 says almost all the laws of elementary arithmetic are consequences of the axioms defining a field. So prove in particular that if F is a field and alpha, beta, and gamma belong to F, then the following relations hold. And if you look at these relations, A through D, these are, or A through G rather, these are things that we quite often take for granted when we do algebra, but as we see in a second, all of these things come from the definition of a field. If something is a field, we can prove these things. So let's start with A. A says 0 plus alpha equals alpha. Well, if we go up here, for addition, a field, by definition, says that there exists such a 0, such an object, such that any number plus that 0 will equal to alpha. Right? That's the definition. So if I look at what he's saying here, 0 plus alpha equals alpha. This is the definition. The only difference is he uses the commutative property here. Notice here we have alpha plus 0. Here we have 0 plus alpha. Well, we know that by definition of a field, the plus is commutative. So I can rewrite this as alpha plus 0, and I'm back to the definition right here. So the first problem, part A in the problem, is immediate. Okay. For part B, it says if alpha plus beta equals alpha plus gamma, then beta and gamma need to be the same. Let me actually do an example for that. Let me scroll down. Okay. So here's what we have. Part B says if I have alpha plus beta, and I'm told that this is equal to alpha plus gamma, then beta and gamma have to be the same. Why? Well, we know we're in a field, right? Let me actually write out an example as well so we can see here. Let's say I have 2 plus x1 equals 2 plus x2, okay? And these numbers will be coming from the real number line. That's the field that I'm using, okay? Now, because I'm in a field, I know that any one of these numbers, any one of them, has an additive inverse. In other words, there exists a negative 2, a negative alpha. So let me add the negative alpha to both sides of these equations. So I'm going to do negative alpha plus beta, and I add negative alpha to the right side as well, plus alpha plus gamma. And I'm going to do the same in this concrete example in the real number line so we see how it works. Again, we know that we're in a field, so the 2 has an additive inverse. Let's add that to both sides. Negative 2 plus x2. And now we see that the negative tend to cancel. Negative 2 plus 2, they cancel. And by cancel, I mean negative 2 plus 2 by definition of a field. That gives me the additive identity, the 0, right? And 0 plus anything, again, by the properties of our field, 0 plus anything is that thing again, that my number doesn't change. And same on the right side, 0 plus x2 is just x2. These are the rules of algebra that we're familiar with. Now, same in the abstract case, negative alpha plus alpha. That gives me the 0. Now, notice that I'm in an abstract field. The 0 might not be the number 0 we're familiar with. So one way of writing this is 0 subscript f, meaning that whatever field I'm in, this symbol represents the additive identity of that field. So 0 of that field plus beta equals, again, 0 of that field plus gamma. Now again, because we're in a field, the 0 is my additive identity. So 0 plus beta will just be beta again. And same with the right side. 0 plus gamma will just be gamma. And we've proven that these two are equal. So what does this property really give me? You've probably done this in middle school algebra or elementary school, where you just cancel these two things. The 2's, you can just cancel them, right? You've done this. Why are you allowed to do that? Well, because in reality, you're just adding -2 to both sides. Well, how do you know that a -2, this idea of a -2 exists? Well, you know that because you're in a field. You're in the real number line. So you know that the additive inverse exists. And there you go. We've proven that beta equals gamma. Okay, so go into C here. C says prove that alpha plus, now in parentheses we have beta minus alpha equals beta. Let's write that out. So we have alpha plus beta minus alpha equals beta. This is what we need to prove. And as a concrete example in the real number line, we might have 2 plus in parentheses, let's do 5 minus 2 equals 5, excuse me, not 2, definitely doesn't equal 2. 5. Okay, so how would you prove it here? Well, you could do 5 minus 2, and that would give you 3, and then you do 2 plus 3, and that'd give you 5, and that's all fine. But what we want to rely upon is that we see an alpha and a negative alpha. Let me rewrite this like so. B, instead of writing minus alpha, we know that we can write plus negative alpha. That's essentially the same thing. Now, why am I doing this? Because I know we're in a field. We're in some field F, and these symbols are quote-unquote numbers from that field. And in a field, the plus is associative. That was part of the definition of a field. If it's associative, I can drop these parentheses. So I do that. Alpha plus beta plus negative alpha. And we need to prove that that equals beta. This is what we're trying to prove here. Well, why did I do that? Because I also know that in a field, this plus sign, this whatever the addition is, it's commutative. So I can swap these two, the beta and the negative alpha. So I can have alpha plus negative alpha plus beta. Why did I do that? Because we know that negative alpha is the inverse of alpha, right? That's the definition of what negative alpha means. When I add them, I get the 0 in that field. So the 0 of that field plus beta, the question is, does that equal to beta? And we know that because this is the additive identity, it's the 0 of that field, adding it to anything leaves that thing unchanged. And so we get beta equals beta. Okay, so we've proven that as we needed. Now, how would you do all this in this concrete case, on the real number line? Well, let's try to follow the same steps. First, because we're associative, our plus is associative, I can drop these parentheses. So 2 plus 5 minus 2. Then what I'm going to do is I want to put the -2 next to this 2 so I can cancel them, right? So they can add and give me the additive identity, the 0 in my real number line. So I write 2 plus 5 plus -2, just to make things explicit. Now I use the commutative property of addition. I swap them. There we go. And now 2 plus -2, we know that gives me the 0 in my field, in my real number line. And this is the regular number 0 that we're familiar with. And adding it to 5 gives me 5. And I'm done. So this right side is a specific case. This is basic introductory algebra or arithmetic, I guess, that we've been doing. The left side generalizes this concept to any field. It doesn't have to be the real number line. Okay, moving on to D. We need to prove that alpha times 0 equals 0. And the reason I'm skipping this middle portion right here, the 0 times alpha, is because by definition of a field, this product is commutative, right? If we go up, we see that the product is right here, the property 1, it's commutative. So 0 alpha times 0 is going to be equal to 0 times alpha by the definition of the field. So all I need to prove really is alpha times 0 equals 0. Okay, how are we going to do that? Let me scroll a bit down. Actually, to the side right here. Okay. So I need to prove that alpha times 0 equals 0. And in a specific example, in the real number line, we can say we need to prove that 4 times 0 equals 0. So this might sound completely insane, right? We all know that 4 times 0 is 0. But remember, we're working now in the abstract field. And here things are not that obvious because these zeros are not the number 0 we're familiar with. They're some concept, right? So let's see how we can prove this. Well, let's keep the alpha where it is, times. Now look what I'm going to do. The 0 of my field, I'm going to rewrite it as the 0 plus the 0. Why can I do this? Well, because look, 0 we know is the additive identity, right? Adding it to anything doesn't change that thing. So adding 2 of my additive identities doesn't change this right one. It still gives me the 0, which is what I have originally. So these two expressions, the expression in the parentheses and my 0 of the field, are the same. Okay? But what does this give me? Let's see. Now I'm going to use the distributive property. I have a product here and I have an addition, so I can distribute. So I get alpha times, actually, let me write that on the new line here. I get alpha times the 0 of my field plus alpha times the 0 of my field. Okay, and where did we get this expression from? This expression, where did we get it from? We got it from here, from the left side. So this is alpha times 0 of the field. Okay, so now because we're in a field, we know that this number, whatever this expression is, whatever this quote-unquote number is, it has an additive inverse. We're in a field, everything has an additive inverse. Let's add that additive inverse to both sides. So here it is, negative of the alpha times 0f plus whatever I had before. And I added it to the left side, so I have to do that on the right side as well. Negative alpha times 0 of my field plus alpha times 0 of my field. And now look what happens. Because this is the inverse of alpha times 0f, they cancel, right? They add to my additive identity, to the 0 of my field. Then I have the plus this alpha times 0f equals, well, what do I have on the right side? I have negative the additive inverse of alpha 0f plus alpha times 0f. So they cancel, right? I have the additive inverse plus the original version. So that gives me the 0 of my field. Now, again, on the left side of the equation, I have the 0, the additive identity, the 0 plus some number, let's call this a number. Now, because this is the additive identity, this number doesn't change. It's still alpha times 0 of my field equals 0 of my field. And I've proven what I set out to prove, that alpha times 0 of my field equals the 0 of my field. In this specific example, what it means is that you give me any alpha. In other words, you give me any number from my field, 5, 10, 11, whatever. In this case, I've picked a 4. If I multiply that by the additive identity in my field, the 0, in other words, of my field, I'm going to get 0. And that's what we just proved here. Okay, and we proved it by writing the 0 as 0 plus 0 using our distributive property. Then adding the additive inverse of this expression to both sides. There it is. I added the additive inverse to both sides. This pair cancels. This pair, the pair on the right, also cancels. And we're left with 0 plus alpha times 0 equals 0. So the final line says alpha times 0 equals 0, and we're done. Okay? So I can write now confidently, I can say 12 times 0 equals 0, anything I want, even complex numbers, right? I could say, for example, 3 plus 4 I times 0 equals 0. I can confidently say this because I know complex numbers form a field. Here's a number from that field. I'm multiplying by the 0 of that field. Technically, the 0 is 0 plus 0I, right? It's the 0 in the complex numbers. I multiply, and I get back the 0 in the complex numbers. Okay. So moving on to the next problem here. E says negative 1 times alpha is negative alpha. So what does this really say? It says if you take negative 1 and multiply it by any number in your field, you're going to get the additive inverse of that number. Okay, how can I prove this? Let's see. If this expression is true, if in fact negative 1 times alpha is the additive inverse of alpha, then if I add negative 1 times alpha, if I add this expression to alpha itself, I should get the 0 in my field. Why is that true? Because look, if negative 1 times alpha is in fact the additive inverse of alpha, then if I add alpha to it, I should get back to my additive identity. That's the definition of additive inverse. So I'm saying if that statement is true, then when I add it to alpha itself, I should get back to the additive inverse. Okay, this line is what we need to prove. So how do we do this? Well, the nice thing is that we know, this is a product here, by the way, we have distributive property, right? So I can factor out the alpha on the right here. And if I factor it out, what am I left with? I'm left with negative 1 plus 1 from here. And negative 1 plus 1, well, negative 1, that's the additive inverse of 1. So adding them gets me to my additive identity, the 0. And we just proved a second ago that 0 in my field times any other number in my field will give me a 0 in that field. So I'm done. Okay? I just proved that if I take this expression, negative 1 times alpha, and I add alpha to it, I get the 0 in my field. So that by definition, that means that this expression is the additive inverse of alpha. In the concrete case, what this means is that in the real number line, if I take negative 1 and let's say I multiply by 5, is this the additive inverse of 5? So is this the inverse of 5? How do we check? Well, let's add the 5 to it. Like we did here, we added the alpha. Here, let's add the 5. Now let's invoke distributive property. Let's factor out the 5. And we're left with minus 1 plus 1. Minus 1 plus 1, those are inverses. They add to the 0 in my field. That's the regular number 0 we know of. And 0 times 5, again, we know is 0. We're done. Okay, so notice the only reason we can do this seemingly harmless operation that we've been doing throughout all of our K-12 education is because of this property of the field, because of distributive property of the field. If we didn't have any of these properties, we could not do these operations. We couldn't, for example, factor out. We wouldn't have distributive property. Okay, so moving on, we're on F now. So F, we need to show that negative alpha times negative beta is alpha beta. Okay, so one way to do F is to invoke E, because we just proved E, we can use it. So in other words, I can rewrite negative alpha as negative 1 times alpha. So let me do that. Let me first write out the problem here. So we want to prove that negative alpha times negative beta is alpha beta. And invoking the property we just proved, I'm going to rewrite negative alpha as negative 1 times alpha. And I can do the same for negative beta, right? So -1 times beta. This is what we need to prove. Now, we know the product is a commutative operation, right? I can swap things. I can swap the order around. These are all products. So let me I can move the negative ones next to each other. And I can put alpha and beta next to each other. So I'm almost there, right? I'm almost close. I just need to prove that -1 times -1 is in fact 1. Okay, so going back, um, going back to our operation here, we see that -1, invoking e here, -1 times any number is the additive inverse of that number. That's what e says. So here I have -1, there it is, times this number here. Let's call this a for a second. So property E just said that this should give me the additive inverse of E. I mean of A. Additive inverse of A. And what is A? A is -1. What is the additive inverse of -1? Well, it's +1. So this expression, -1 times -1, gives me +1. Okay. Now 1 is my multiplicative identity. That's the property of the field. This is my multiplicative identity in my field. Whatever that number is, this is not my regular number 1, right? It's my multiplicative identity. So 1 times alpha times beta. 1 times alpha, we can do that first by associative property. It doesn't matter which multiplication I do first. This associative property is, again, property of a field. 1 times alpha is my alpha, and alpha times beta is what I'm left with in the end, which is what I needed to get. Okay? So when we've proven this result. So in other words, to prove f, we used e. And to prove g, what is g? G says if alpha times beta is 0, then either alpha or beta is 0. Okay, so we have alpha times beta equals 0. The goal is to prove that either alpha has to be 0 or b has to be 0. They can't both be non-zero. In the real number line, this corresponds to saying, okay, if I say 3 times x equals 0, then you know for a fact x has to be 0. X can't be anything else. So let's see how it works. Now, the way this proof works, we're in an abstract field here. The way this proof works is it's a proof by it's a proof by assumption. Let's assume that alpha is non-zero. Okay, so let's assume that alpha is not 0. 0 of my field. Again, it's not the number 0, but it's the 0 of my field, right? If it's not 0, by the property of fields, we know, let me scroll up here, to look at property 4. To every non-zero scalar, there corresponds a unique inverse, such that when I multiply them, I get to the multiplicative identity in my field, the 1 in my field. So let me invoke that property. If I'm saying alpha is not 0, by the property of fields, there exists some multiplicative inverse of alpha, which I'm going to now multiply on both sides of the equation. So 1 over alpha, that will be my multiplicative inverse, times alpha times beta equals 1 over alpha times the 0 of my field. 1 over alpha is the multiplicative inverse of alpha. So we know this gets me back to the multiplicative identity in my field. Times beta equals, now this, the right side, we just proved a couple I guess sections ago that anything in my field times the 0 in my field will give me back the 0 in my field. Okay, now we know on the left side, looking at the left side, we know that the multiplicative identity, the 1, times anything in my field gives me back that element, that beta will not change. That's the definition of a multiplicative identity. And we get beta equals the 0. Okay, so what did this tell me? We assumed alpha was not 0, and we got that beta has to be 0. I leave it up to you guys. If you're interested, try to prove for yourselves that if you assume that beta is not 0, then you will get that alpha has to be 0. So at least one of these two will have to be 0 for this equation to be satisfied. Okay, now doing this in this concrete example in the real number line, we have 3 times x equals 0. We see that 3 is not 0, so it has a multiplicative inverse. We all know what it is. It's 1/3. So let's multiply 1/3 on both sides of this equation. 1/3 times 3. Again, we know when we multiply them, we get the multiplicative identity, the 1 times x equals, and 1/3 times 0 we know is 0. And 1 times anything we know is that thing. It doesn't change, so we get x equals 0. We're done. So if the 3 was not the 0, then the x had to be the 0, just like in this abstract case. Okay? And what property of fields did we use to prove this? Well, we used the fact that any non-zero element, alpha, has a multiplicative inverse 1 over alpha. Okay, this is not trivial. This doesn't have to be true. It's not like a God-given right. This is a property of fields. Okay, moving on to the next problem here. So let's look at problem 2. This one's quite interesting. This is a question. Is the set of all positive integers a field? Okay. And Thomas goes on to say here that what the operations that he's talking about are the regular addition and multiplication that we know. So that's what he's talking about, regular addition and multiplication. And if we assume those, do we have a field? So let's check. So we are talking about integers here. All right. So integers are, of course, -1, 3, 4, etc., 5, 0, blah, 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 right? We denote them this way. This z here. These are integers. Now we're going to use the integers and the regular addition and multiplication, because we know for fields we need 2 operations that are commutative and associative, right? So the 2 operations we're going to be considering are the regular addition and multiplication. Okay, so what are the properties we need to satisfy? Let's go back to the properties of a field. So for addition, we need to be commutative. Well, we know that's true for integers. 3 plus 4 is the same as 4 plus 3. That's good. We need it to be associative. In other words, we need to be able to move the parentheses when we're adding stuff. We know that's true for integers with addition, right? 3 plus 4 plus 5 is the same as 4 plus 5. Doing that first and then adding the 3. Addition is associative. There exists a unique scalar 0 such that any number plus that 0 gives me the original number back. Well, we know that that's our 0 here. 0 plus any number, 0 plus any number is that number. So we do have an additive identity. We have a 0. Okay? What about 4? For every alpha, we need to have an additive inverse that gets me back to the 0. We also have that because if we pick an alpha, let's pick let's pick 4. Well, do I have an additive inverse for 4? Yes, I have the -4. If I add them, I do get back to my additive identity. And that is the case for any number in Z, for any integer. So the addition is satisfied. All the properties of addition are satisfied. So we go to the B section. Let's check the product. What do we need for the product? It needs to be commutative. Is multiplication of integers commutative? Yes. We need it to be associative. Can I move the parentheses when I'm multiplying integers? Yes. Do I have a non-scalar, quote unquote, 1, called 1, such that any number times that 1 gives me that number back? Yeah, I do. It's actually the numeral 1. It's the integer 1, right? Because if I multiply it by any number on either side, I get that number back. Okay? So we have that. And property 4 says to every non-zero scalar, we should have an inverse such that when I multiply them, I get back to that 1, to that multiplicative identity. Do I have that? Now, this is a problem because let's say I pick the number 5. Let's say I pick the number 5. This is my alpha. I've picked an alpha of 5. I need another number in the set of integers. So in this set of integers, I need another number such that when I multiply this 5 by that number, I get my multiplicative identity. Now we know what this a should be. We intuitively want to say, oh yeah, a needs to be 1 over 5, and that's true, but 1 over 5 is not an integer. It's not in this set. Okay, so here is the number 5 that does not have a multiplicative inverse. There's no integer that I can multiply 5 by and get back to my multiplicative identity, get back to 1. So z is not a field. Z is not a field. Now, under these two operations, under plus and product, it is crucial to specify this because you might come up with a different notion of addition, a different notion of multiplication, such that all these properties hold. And then z, with those two operations that you've defined, would be a field. But with the regular addition and multiplication, it isn't, because multiplication breaks on us. The numbers don't have multiplicative inverses. Okay. So to answer Mr. Ramos' question here, no, z is not a field under the regular addition and multiplication. Okay. So what about the set? And okay, actually, so he goes on, he mentions this as well. He says, so what about the set of all integers? We just said it's not a field. What about the set of all positive integers? Positive integers meaning from 1 and on. Is this a field? Well, what is the problem with the positive integers? Let's see. Let me do this. Let me erase some of this stuff here. So we have some space. So when we think about all the positive integers, again, it's a good idea to start thinking about the properties of the field. What do we need to satisfy for this set to become a field? We need two operations, right? Addition and multiplication, and we're thinking about the regular addition and multiplication that we know of. Now, what can go wrong with positive integers? Let's see. Suppose we pick a number from there. Here's a set of positive integers. This is going to be the number 1, 2, 3, and so on. Notice 0 is not included. Let's say I pick a number from there, 3. Fine. And now I say, okay, give me the additive inverse of 3. We know that if, according to the properties of fields, any number from that field needs to have an additive inverse. That gives me back the identity. Okay. Well, even before we talk about inverses, what is the additive identity? Okay, additive identity should be some number, some quote-unquote 0, such that when I add it to any one of my numbers, I get that number back. Now, if we're talking about regular addition here, the only number that can do that is the 0, right? But is 0 in my set? No. 0 is not even in there. I don't even have the additive identity here. So that alone breaks the property of fields. Okay, we can't even talk about inverses because if I have an inverse, it gets me back to the additive identity, to my 0, but I don't even have the 0 there to begin with. So right there, I stop and I say z plus is not a field under the regular addition because my additive inverse is not there. Or rather, my additive identity, my 0, is not there, and we're done. Okay, so see here, the third part of the question is actually a fantastic question. This is the one you should think about. If you have time, it will really challenge you, and it's a great question to think about. It says, can the answers to these questions change if I redefine addition or multiplication or both? So let's stick with all of the integers. So you have all of the integers, all of them. Negatives, positives, -3, -4, 0, 1, blah, 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 etc. Everything. But now you're allowed to define your own addition and your own multiplication. For example, you might say that if I take -3 and plus it with, and let's say this is the addition that Sam defines. I'm going to do plus underscore Sam, subscript Sam. And let's say -3, Sam's plus 7 equals 100. Okay. Sam has defined this plus. This is a perfectly valid thing to do. This is no longer the regular addition that we know. It's a different operation altogether. And maybe Sam defines multiplication in some way as well, such that -3 times 7 is 4. Okay. So you're allowed to define how addition, your own addition, and multiplication work. But what you want to do is you want to define them in a way that makes integers a field. So what are the properties of the field? Well, we just talked about the properties of the field, right? Your addition and your multiplication should be commutative and associative. Both of them, well, addition should have, and both of them should have identities. Addition should have the quote-unquote 0. Multiplication should have the quote-unquote 1. For addition, every number in your field should have an inverse that gives you back the 0. For multiplication, every non-zero number should have an inverse. And the distributive property should be satisfied. Okay? So if you can find such two operations and use them with the integers, that'll give you a field. So think about if that's possible, see if you can do that. Okay, and finally, I want to talk about problem 3 here. This is absolutely phenomenal problem, and I mean, if you studied this stuff in school and college, you've probably done this many times. I actually thought about this problem this morning, and I completely forgot about how to approach this. It took me some time, but it's actually really interesting exploratory work. So let's do this one. This will be the last problem, and we'll end the stream here for today. And then we'll do a quick Q&A. Okay, so what does the problem say? It says let m be an integer bigger or equal to 2. Okay, so let's write that down. We're going to have m bigger or equal to 2. And we're going to define this set z underscore m. What is this set? This is the set of all positive integers less than m. Okay, so he says all positive integers, but noticing with 0 in there. So that might be a little weird, but there's Helmos. So we're not gonna doubt Paul Helmos, and we're just gonna write 0, 1, 2, blah blah blah, m minus 1. This is what z subscript m means. If alpha and beta are two numbers in that set, let alpha plus beta be the positive remainder obtained by dividing the sum by m. Okay, so he's defining his addition, and notice how he defines it. He says, if you take two things in this set, let's call them alpha and beta, how are you going to add them? Well, you're going to add them normally, and then you're going to look at the remainder after you've divided by m. So I'm going to use the computer programming notation here. I'm going to put %. This just means give me the remainder after division by m. Okay, so if you think about it, for example, if you take two numbers, let's say my m is, let's stick to concrete examples. Let's say my m is what? Let's say 6. So I'm looking at z6 in this specific case. So this is 0, 1, 2, 3, 4, 5. If I take two numbers here and I look at the remainder after I divide by 6, the result is definitely less than 6, right? So if you take, for example, 4 plus 5, those two are in here in this set, and I look at the remainder after division by 6, the remainder after I divide 9 by 6 is 3, right? There it is. Obviously, the remainder is supposed to be less than 6. That's why it's a remainder. So if it's less than 6, it is in this set, because this set contains all the integers from all the non-negative integers from 0 up to 6, not including the 6. So anything less than 6 is here. So I know for a fact that when I do this operation that he's defined, I'm going to get a number that is in this set. I'm safe in that regard. I'm not going to get some number that is not here, right? So that's my addition. Now for multiplication, it defines it exactly the same way. It says you take the product, the regular multiplication, you divide that by m, and you take the remainder. Okay, so in this, sticking to this example, if I were to multiply these two numbers, and then I would say, okay, what is the remainder after I've divided by 6? Well, 4 times 5 is 20. And if I divide 20 by 6, the remainder is 2, right? 3 times 6 is 18, and there's a remainder of 2, and there's my 2. Again, because I'm taking a remainder, I know that it's going to be less than 6, so I know that it's going to be in this set. So far, so good. We've defined two operations, and the addition is just add these numbers, and then take the remainder after division by 6. Multiplication is just multiply those two numbers, take the remainder after division by 6. In the abstract case, we're dividing by m, of course. There we go. Okay, so what do I need to do? I need to do the following. It says, let's see, positive by m. Okay, it says prove, and we're only going to prove this a here. It says prove that z subscript m is a field if and only if m is a prime. Okay, so my job is to prove that this z subscript m is a field only if m is prime. Okay, so if that is true, this z subscript 6 should not be a field, right? Because 6 is not prime. Let's check that it's not, why is it not a field, right? What goes wrong here? All right, so let me prove the general case first, and then we'll come back to the example. All right, now if you don't know how to approach this problem, one way to think about it is this. You're saying, let's first take a look at the addition. Okay, if I'm adding two of the numbers that are in this set, can I get, for any alpha that I pick, so I'm picking the alpha. Let's say in the specific example, I pick the, what should I pick? I pick the 2, let's say. 2 will be my alpha. If I pick any number in this set, can I find another number, let's call this beta, I don't know what the beta is, can I find another number such that when I add them, the remainder after I divide by 6 is 0? In other words, do I have additive inverse for any number that I pick from here? Well, in this example, you say, yes, you do. Beta should be 3, right? Because beta should be 4, because 2 plus 4 gives me 6. And if I divide 6 by 6, I get 1, a clean 1. There's no remainder. The remainder is 0, so I got back to my additive identity. And if you say, okay, what if I picked alpha to be something else? Maybe I pick it to be 1. Okay, if it's 1, then add 5 to it, right? You get 6 again. And if you divide 6 by 6, you get 1. There is no remainder. So the additive inverse of 1 is 5. The additive inverse of 2 is 4, right? Notice we don't have a negative 2. We don't have a negative 1. But the notion of additive inverse is still there. The additive inverse of 2 is 4, and that of 1 is 5. So intuitively, it seems like for any number in this set, I can't find an additive inverse. In other words, I can't find a number that I would add to my alpha that would give me a total of 6. Okay? Is that true for multiplication? That's the question, right? If I were to pick any alpha, is it true that I can find another beta in this set such that when I multiply them, and then I do what? I divide by my m, okay? I get back to my additive identity, which is 1. And take the remainder, I get back to the identity. Okay? So in math notation, what this says is, if I take alpha plus beta, for any alpha, is there a beta such that alpha beta is congruent to 1 modulo m? Okay, I'm assuming you've seen this modular arithmetic before. If you haven't, again, modular arithmetic here, all that means is I take the product alpha times beta, I divide that by m. In other words, I divide out all the multiples of m that I have there. So I'm only left with the remainder, and I want the remainder to be 1. Okay? Is it true that for any such alpha, I can find an appropriate beta that does this? All right, so how can we do that? How can we prove that? Let's take a look. Now, suppose, like me this morning, you have no idea how you can systematically prove this step by step. You want to do some exploratory work, right? You want to approach this from an exploratory perspective. You say this, you say, okay, what if I said, here's an alpha, and here's some other beta, some two numbers from this set, any two numbers, non-zero, we're talking about product here, and in a field, when we're talking about products, most times you don't care about the zero because we proved that 0 times anything is 0, so we don't care about that. But these two are any non-zero numbers from my field. I'm going to call this one beta subscript 1. Okay, now, if I do this product, this product is my modulo here, modulo m. Suppose I get some number c, modulo my m. And let's say I take the same alpha, and I take another number from here, some beta 2. And let's say this also gives me the same c modulo m. Okay? So what I'm saying here, I'm saying you give me an alpha, let's say the 2 right here. Let's say we pick the 2 for alpha. And now I'm saying whatever the betas are, I want two different betas such that this product, when we take the modulo by this m, gives me the same number c for both of them. And what I'm trying to show here, that if this is the case, if both of these products, modulo m, give you the same number c, then what I'm trying to prove is that beta 1 has to be equal to beta 2. There's no choice. And so what that would tell me is that if I keep cycling through these betas, in other words, if I fix the number 2 for alpha, let's say, and I keep cycling through these betas, 1, 2, 3, 4, 5, 6, all the way to m minus 1, these c's that I get will be different for every beta that I pick. If I pick two different betas, I could not possibly get the same c here. And so what that means is that if I cycle through these betas and I'm getting different c's for each beta, then one of these c's has to be this 1, right? Because my betas are cycling from 1 to m minus 1, and for each of these betas, I'm getting a different c. So one of these c's will have to be the 1. And if alpha times some beta gives me the 1, that means that beta is the multiplicative inverse of that alpha, because I multiplied them and I came back to 1. Okay, so let's do step by step. Let's first show this. So I'm saying I fixed some alpha. Now I suppose I have two different betas from this set. I multiplied them by modulo m, and I got the same c. What does that mean, really, modulo m? Well, it means that you have alpha times beta 1 equals some multiple of m. And let's call this p m plus this remainder c. And in the second part, we have alpha times beta 2 equals some multiple, again, of m plus c. Okay, so now one thing I can do is I can say, well, I see a p times m plus c. Here I see a q times m plus c. Both of them have a plus c in there. So maybe I can do some operation on these two equations to get rid of the c's. Okay, so let's do subtraction. Let's subtract the right equation from the left one. Okay, so what do we get in that case? We get alpha beta 1 minus alpha beta 2 equals, well, c minus c, that will cancel. So we'll be left with pm minus qm. Let's do some factoring here. Let me factor out the alpha. Again, I know I can factor it out. This is the distributive property that I'm using here. And we're in a field, so we know we can do this. Okay, here I factor out the m, and I have p minus q, like so. Okay. Now, my job was to prove what? My job is to prove that B1 equals B2, because I've assumed that both of these products give me the same C. So I want to prove that B1 does equal B2. How do I do that? Let's see here. Okay. So let's suppose, okay, let's suppose that M is prime. So we're approaching the problem from that direction. We're initially supposing that M is prime. So let's suppose M is prime. Now, if M is prime, M times P minus Q, this is some multiple of this prime here. Okay? Now, notice that my numbers start from 0 and they go up to M minus 1. They do not include M. So both alpha that I pulled from this set and beta 1 minus beta 2, both of which are also numbers pulled from this set, are smaller than M, right? They're both smaller than M. So in the prime decompositions of these two numbers, the alpha and beta 1 minus beta 2, M does not exist. This number does not, this prime number, M, does not exist in the prime decomposition of either alpha or beta 1 minus beta 2, because both of those are pulled from this set, and all these numbers are less than M. If M is prime and it doesn't exist in the prime decomposition of either of these numbers, then their product cannot equal a multiple of M, because we know M is not in their prime decomposition. The only way this can happen is if P minus Q and beta 1 minus beta 2 are 0. Because if they are both 0, then yes, this equation is satisfied. That is the one trivial case in which these two equations are satisfied, even though alpha and B1 alpha and B1 minus beta 2 don't have M in their prime decomposition. That's the one case. So in other words, B1 does equal beta 1 does equal beta 2. So one more time, if we assume that M is prime, then beta 1 has to be equal beta 2, because neither alpha nor beta 1 minus beta 2 have M in their prime decomposition. So this is the only case in which this equation holds. And if beta 1 equals beta 2, what did we show? We showed that if you fix your alpha to some number from this field here, or from this set here, and you start cycling your betas through these numbers from 1 to M minus 1, each time you will get a different C. Each time of the product, you will get a different result, because if the results were the same, your betas would be the same, right? Their difference would be 0. They would be the same. So if you take different betas, your C's will be different. So that means as I cycle my betas, for every beta, I get a different C, which means one of those C's will have to be this one. I'm cycling through them. How many betas do I have? I have 1, 2, 3, 4, all the way to M minus 1. That's M minus 1 betas. And for each one, I get a different C. How many C's is that? That's M minus 1 C's, right? So that's M minus 1 C's. So we know that one of those C's has to be this one. Okay, now you might say, how do I know that none of those M minus 1 C's is the 0? Maybe the C's are 0, 2, 3, 4, 5, up to M minus 1. Maybe the C's skip over 1. And so I leave it up to you to think about the fact that if I take two things from my field, two non-zero things, and I multiply them, if I take them from the set, and I multiply them, the result will not be the 0 here. Okay, so I leave that up to you. So in this situation, we've shown that C's, for one of these betas, the C will be equal to 1, and that beta will be the multiplicative inverse of alpha. Okay? So this is assuming M is prime. Okay, and you can go on to show the other properties of the field, and you'll see that they're satisfied. And so Z subscript M will be a field if M is prime. I'm not going to show all those properties because they're much simpler to show. This was in my opinion, this was the hardest property to show. And of course, this is not a full-blown proof, but this is some exploratory work to put you on the right path, and you can formalize this yourselves. And again, to recap, what I'm doing here is I'm saying fix your alpha, then start cycling your betas. And what I showed is that if your betas are different, then the results of these products will also be different. They can't be the same C. And so as you cycle your betas, one of your C's will have to be the 1, which means that that beta will be the multiplicative inverse of this alpha. Okay, well, what happens if M is not prime? What happens then? Let's see here. Well, if M is, let me get rid of this. Let me clear the screen a little bit. Let's actually pull over here. All right. So what happens if M is not prime? Well, we're here. This is the equation we have. Alpha times beta equals, what were we doing? C mod M. Right, this is what I had written before, and now we're going to assume that M is not prime. So if M is not prime, that means M is a product. If M is not prime, then M has to be a product of two integers that are smaller than M. Let's call those A and B. Right? That's what non-prime composite numbers, composite integers are. They're just products of two integers smaller than M. Now, these two integers that are smaller than M, these two positive integers, they are in my set because my set contains all the numbers from 0 up to M minus 1. And these two numbers, A and B, they are anywhere from 1 to M minus 1, right? They're somewhere there. They're two non-zero numbers that I've taken. And I'm assuming that M is not prime here. So if I take these two numbers from my set and I multiply them, two non-zero numbers, notice A is not 0, B is not 0. I'm picking A and B. I'm picking them myself, and I'm making sure they're not the 0. And I look at their product under this product that Helmholtz gives us. I look at their product. What is their product? Well, it's M, right? Because M is not prime. It's a composite. So we have two integers less than M such that their product is M. So this product is M here. Now, the product that we're interested in takes the modulo, looks at the remainder after the division by M. So if I take M and I divide by M, what do I get? I get 1. Do I have a remainder? No. So this gives me the 0. Right? I get back to the 0 here. But what does this really say? This says that I took two non-zero numbers, I multiplied them in this crazy old multiplication that we've defined, and I get 0. Is this possible? No. Do you remember when we were showing the properties of the fields here, when we were proving properties of fields, right here, G, we said that if two non-zero numbers, if we have two numbers that multiply and give me 0, then either one or both of them have to be 0. At least one of those numbers has to be 0. We proved this. But in this case, I have two non-zero numbers that I've multiplied, and I'm getting a 0. This cannot happen in a field, hence Z subscript M cannot be a field. Okay, so if, again, where did we start? We said, okay, let's assume M is not prime. If M is not prime, it's a product of two smaller positive integers, both of which are in this set. Let's get those two integers. Let's multiply them under this definition of multiplication. If I multiply them, I get M, and the remainder after the division by M is 0. And because we multiplied two non-zero numbers and got 0, Z subscript M cannot be a field. Okay, so that's that case. So this is where I'll stop. It's kind of I think this is an amazing problem. It's quite beautiful. Now, what you guys should do is you should take this further and write formal proof. There's a ton I hand wave throughout the whole thing just to give you the intuition. Try to formalize this and try to write the full proof. I posted the link to the book in the Discord channel, so you can go and check it out. Yeah, and do ask questions if you have any. Myself and others are there to help. Okay, guys, I'll see you next time. We'll continue with this problem set and into the next section. All right, see you guys later.